Hello everyone, and welcome back to another session of Computational Algebraic Geometry. Last week we were discussing the Fano scheme of lines inside a surface, and now we're going to continue and finish this discussion. Remember that our goal is to show that the Fano variety is reduced, and to show this we were going to study the points on the Fano variety over the dual numbers. What we did thus far is to understand what it means to have certain points on the Grassmannian where point is not over a certain field but over more interesting rings such as the dual numbers. But what we did not do yet was to understand what it means to have a family of lines lying entirely inside a given surface. So that's where we will continue our story. Remember that S is a surface cut out by a polynomial f. F has coefficients in K, F is homogeneous, K was characteristic 0, and whenever I talk about schemes or rings, I mean over K. So a ring B, for example, will be a K algebra, really. Now, as a base for our family of lines, I'm going to take the spectrum of a ring. T is my base, and it's the spectrum of a ring B. So it should be a K algebra because the coefficients of F should make sense within B. Now I can form S times T over K, and this lives inside P3 times T. P3 times T, we wrote this as proj of B, X, Y, Z, W. Here we also have a similar interpretation for S cross T. So we can now write S cross T also as proj of a ring, and it's this ring. So we take the ring generated by the coordinate functions on P3 with coefficients B, and since we can interpret the coefficients of f as in B, my polynomial f can be viewed as a polynomial inside of this ring, and I take the quotient. When you take the proj of this, the only thing that I will care about is that morphisms to P3 will lie or factor through S times T precisely when the pullback of f is 0. So this would agree with our general concept that something is inside S if f vanishes on it. And more generally, whenever f from P3 pulls back to 0, then whatever was going into P3 should factor through S times T. This prompts the following definition. If I take a family of lines over T, spec B, this family of lines lies inside of S precisely when the inclusion from P to P3 factors through S times T. So far so good, this makes sense conceptually. Let's now see what it does to a slightly more explicit family of lines. So I'll suppose that my family of lines lives inside an affine chart of the Grassmannian, so that I can write it down explicitly, and then convert this to something about equations. So within the terminology that we used last week, I'm just saying that the family of lines over T corresponds to a T point or a B point of our often open chart of the Grassmannian. So I call this G0, and therefore I can represent this line with a matrix as usual. And this meant that the pullback of variables was determined by this matrix. So the pullback of the coordinate x on P3 was, let's say, the first coordinate u in P1, y pulled back to v, and so on. Let me write this down. And now what we're asking is, when is this family of lines supposed to factor through S? So S is distinguished by the fact that the polynomial f vanishes on every point on it, and the corresponding notion here should be that the polynomial f pulls back to 0 on P1, B. So the family of P1s over B. But we know what x, y, z, w pulls back to, so we just plug in x, y, z, w with these u, v, etc. And then this should be identically 0. In particular, let's expand this out. So if I were to write this expression in FUVs as CD of B times UD plus CD minus 1 B UD minus 1V, etc. Then what I'm saying is that these coefficients should be identically 0 in the ring B. Now what's important here is that these coefficients could have been cooked up as purely polynomial expressions in 4 variables, and then I would have just plugged in the values bij's to these variables. So let's consider this universal expression first, and then we will remember what we were trying to do here. Start by identifying the affine chart of the Grassmannian with the spectrum of a ring of polynomials. And then, just like before, I construct this expression using f. I'm going to expand this out with polynomial coefficients in a polynomial in UV. So I write CD of A, UD, etc. plus C0, VD. So just like before, except C0 is C0A. And each CJA is a polynomial. And what happened previously when we were using some arbitrary ring B was that we had just evaluated these polynomials in our sort of variables, numbers, bij's. So that prompts the following definition for our affine part of the Fano scheme of lines in S. So I take the 0 locus of these polynomials, or as a scheme, I mean the spectrum K, A11, A22, modulo the ideal generated by CDA, C0A. So that's the definition of this affine Fano variety. And of course, schemes can be patched together by their affine charts. And what I'm doing clearly does not really care about the fact that I've used the first affine chart of the Grassmannian. I could have used any of the other affine charts, and I could have patched together the Fano varieties that I've formed this way. Okay, so globalizing this definition, we find the Fano variety as something that is locally these fs zeros for which I've written down the polynomials. Now the interesting thing here, and the discussion we've made in the previous section, is that for sure any family of lines gives me a family of lines inside of S if the pullback of these polynomials CDs, CDAs is 0 on the base. So we make the following observation. Any family of lines in P3 is in fact a family of lines inside of S when the corresponding morphism from the base of the family, let's say T, that goes to G24, factors in fact through fs. And this is on affine charts, what we were trying to understand up until now. On affine charts, this just means that these polynomials CJAs should vanish, but that is nothing but saying that on that affine chart, your map factors through fs0. And this observation is formally just saying that fs is a fine moduli space for the family of lines in S. And if you can, it makes sense to fill in the details of the proof of this observation on how you would globalize. But the upshot of this section is to say that, okay, fs captures the family of lines inside of S. In particular, if lines inside of S cannot be perturbed, then points in fs cannot be perturbed, which means fs is reduced. And it will be zero-dimensional when this condition holds. And we will see that no line can be perturbed precisely when the surface has degree at least 3. So let's start thinking about this.